engineer the ultimate breakthrough vehicle, absolute mass was required. The Tiger II was a mobile fortress governed by extreme physics. Before armor or weaponry could be mounted, the foundation had to support an unprecedented 68 tons. This required scaling the geometric footprint to extreme proportions. The foundation began with the KGS-73 combat tracks. These were not standard links, but massive, heavily cast manganese steel plates. Each combat link measured an astonishing 800 millimeters wide. This extreme width was a mathematical necessity to prevent the vehicle from sinking under its own weight. To distribute this colossal mass evenly across the wide tracks, engineers utilized the Schachtellaufwerk, a highly complex system of overlapping, interleaved road wheels. This suspension required staggering the wheels across distinct geometric planes. Inner, middle, and outer rows were densely packed to maximize the number of contact points on the track. Inside the hubs, the standard bearings were entirely inadequate. Immense heavy-duty roller bearings were engineered to withstand the crushing gravitational force of the chassis. These wheel clusters were mounted to massively reinforced forged steel swing arms. These arms pivoted through the hull, transferring the kinetic shock inward. The internal torsion bars were scaled to match. Spanning the entire width of the wide hull, these highly tempered steel rods featured an extreme diameter to handle the unprecedented load. When traversing rough terrain, these rods twisted along their axis. The red vectors illustrate the staggering amount of shear stress these internal springs were mathematically required to absorb. This overlapping geometry was duplicated across 9 independent stations per side. The result was a continuous, dense wall of steel wheels supporting the chassis. The 800mm combat tracks were then wrapped around the assembly. Tensioning this immense weight required precision mechanics at the rear idler wheel. This extreme complexity solved a critical physics problem: flotation. The overlapping wheels and ultra-wide tracks mathematically distributed the extreme mass, preventing the fortress from sinking. The math was undeniable. Despite weighing 68 tons, its ground pressure was calculated at just 1.05 kilograms per square centimeter, comparable to vehicles half its weight. The foundation of the Apex Predator was established, a colossal, perfectly distributed geometric footprint. Now, it was ready to receive its impenetrable vault. To protect this colossal foundation, engineers abandoned vertical architecture in favor of a mathematically optimized, highly sloped armored vault. The primary defensive plane was the upper glacis, a massive single sheet of rolled homogeneous steel machined to a base thickness of 150 millimeters. However, absolute thickness alone was not the defining factor. The plate was deliberately angled at exactly 50 degrees from the vertical axis. This slope geometrically multiplied its defensive capability. A mathematical line-of-sight algorithm calculating horizontal penetration reveals an effective depth of over 233 millimeters. When subjected to kinetic impact simulations, this geometry acted as an impenetrable mathematical shield. High-velocity kinetic vectors failed to bite into the extreme angle, forcefully deflecting upward and harmlessly dissipating their energy into the atmosphere. The lower glacis was similarly angled at 50 degrees, utilizing a 100mm plate to seal and protect the vital front transmission architecture. Even the lateral flanks were optimized. The upper side hull featured 80mm plates sloped at 25 degrees, extending outward to maximize side impact deflection. To assemble these massive slabs, complex interlocking joints were machined and fused with deep, multi-pass weld seams, ensuring absolute structural integrity under extreme stress. 40mm thick plates sealed the upper and lower boundaries, finalizing the completely enclosed geometric citadel. Inside this vault, the ergonomic space was vast. The wide sponsons overhanging the tracks provided critical internal volume for the crew and internal systems. This specific geometry allowed for the integration of heavily protected ammunition matrices directly along the hull walls, readily accessible but completely shielded. To preserve the absolute structural integrity of the front glacis, operator hatches were geometrically relocated. They were cut exclusively into the roof plate, eliminating frontal weak points. But this extreme ballistic protection demanded an incredible physical toll. The armored hull alone contributed massive, uncompromising weight to the vehicle's footprint. The sloped vault was complete, an impervious steel fortress that mathematically negated almost all contemporary anti-tank vectors from the frontal arc. To propel this 68-ton fortress, immense mechanical energy was required. The heart of the Tiger II was the Maybach HL-230P30, a massive 23.8-liter V-12 engine. Inside the cast iron block, 12 massive pistons operated in flawless synchronization, converting rapid internal combustion into raw rotational torque. Operating at 3,000 revolutions per minute, this engineering marvel generated a staggering 700 horsepower. By any standard automotive metric, it was a titan. However, a critical mechanical paradox emerged. Pitting 700 horsepower against 68 metric tons resulted in a severely underpowered ratio of just 10.3 horsepower per ton. This mathematical reality translated directly to dynamic kinematics. The vehicle's acceleration vectors were severely stunted, making it sluggish and unresponsive from a standstill. Simply to maintain basic forward momentum, the Maybach power plant had to be driven relentlessly at its absolute maximum redline. Operating an engine perpetually at peak capacity generated catastrophic thermal stress. The massive block became a furnace, threatening the integrity of its own geometric tolerances. To prevent a complete meltdown, massive dual radial fans were integrated into the cooling system. They aggressively pulled dense vectors of cold air through heavily armored roof gratings. Despite their size, it was a thermodynamic losing battle. The sheer volume of thermal energy generated by moving 68 tons frequently overwhelmed the cooling capacity, leading to frequent material fatigue. This struggle extended through the entire drivetrain. The immense torque required to rotate the tracks placed unimaginable shear loads on the central drive shaft. At the front, the 8-speed Maybach V-12 transmission received this force. A highly sophisticated piece of engineering constantly pushed to its breaking point just to shift the vehicle's mass. Even steering was a monumental task. The double-radius steering gears suffered immense frictional wear when forced to pivot the tracks against the resistance of the Earth. Feeding this perpetually overstressed engine required an astonishing volume of high-octane fuel. The 860-liter internal tanks were drained at a catastrophic rate. This extreme consumption mathematically strangled its strategic mobility. The vehicle was tethered to a severely restricted operational radius of barely 170 kilometers on roads, and far less off-road. The foundation was an overburdened logistical nightmare. To justify this immense mechanical and thermal cost, the vehicle had to carry a weapon of apocalyptic lethality. To house an apocalyptic weapon, the hull required a massive geometric cutout. A staggering 1,850mm turret ring was machined into the roof plate. Onto this ring descended the production turret, a colossal armored citadel designed by Krupp, mathematically optimized for ultimate deflection and internal volume. Early prototypes featured a curved frontal geometry. However, ballistic simulations proved this curve acted as a fatal shot trap, mathematically deflecting kinetic energy directly down into the thin hull roof. To eradicate this flaw, the production turret utilized a completely flat, slightly sloped frontal plate. Incoming vectors were now forcefully redirected safely away from the chassis. This flat geometric plane was machined to a staggering base thickness of 185 millimeters, a virtual anvil of solid steel. This defensive logic wrapped around the entire structure. The 80mm sidewalls were aggressively sloped inward at 21 degrees, maximizing lateral deflection. Beneath this fortress, a rigid tubular basket was suspended. This rotating floor physically isolated the turret crew from the dangerous, high-torque drive shaft spinning inches below their feet. Inside, the sheer scale of the turret permitted flawless ergonomic zoning. The volume was algorithmically divided. Commander elevated at the rear, gunner left, loader right. The commander's position was capped by a heavily armored cast steel cupola. Unlike earlier designs, it featured 7 low-profile periscope blocks angled for maximum protection. These 7 optical nodes cast a flawless, mathematically overlapping 360-degree vision net, ensuring the apex predator was never blind to its surroundings. To counterbalance the immense frontal armor and future weaponry, the turret featured a massive rear bustle. This geometric overhang served a critical secondary purpose. It acted as a high-capacity ready rack. Vast matrices of heavy ammunition were stored directly behind the loader, mathematically minimizing the reach vector and drastically increasing the rate of fire. The front of the citadel was capped by a colossal bell-shaped cast mantlet, a virtually solid block of curved steel designed to protect the delicate trunnion pivots from kinetic annihilation. To rotate this multi-ton vault, and cranks were obsolete. A powerful hydraulic traverse drive, tapping directly into the engine's power, struggled against the immense rotational inertia. The turret was an unyielding, geometrically flawless fortress. All that remained was the installation of its apocalyptic weapon system. The defining feature of the Tiger II was its apocalyptic main armament. The 8.8-centimeter KWK-43 was mounted directly into the armored citadel. This was not the standard 88 used on earlier tanks. It was an L-71 caliber weapon, featuring a mathematically extended barrel measuring over 6.2 meters long. Balancing this colossal steel tube required immense internal geometry, anchoring it perfectly on heavily reinforced trunnions to ensure smooth, effortless elevation. Feeding this beast required ergonomic optimization. A dedicated trajectory vector moved ammunition directly from the rear ready racks into the breech with maximum efficiency. The ammunition itself was The Panzergranate 3943 cartridge measured over 1.1 meters length and weighed more than 23 kilograms. The massive shell slid into the chamber. Like all advanced German tank guns, it utilized an electrical primer rather than a crude mechanical percussion cap. To contain the upcoming violence, a colossal vertical sliding wedge block slammed upward, sealing the chamber with dense, impenetrable steel geometry. A high-voltage electrical pulse instantly ignited the primer, completely eliminating the mechanical delay of a traditional firing pin. The resulting internal explosion was cataclysmic. A thermodynamic graph registers the extreme chamber pressure required to propel the heavy projectile at supersonic speeds. Forced down the 6.2-meter barrel, the internal rifling imparted an intense gyroscopic spin, mathematically stabilizing the round for hyper-accurate long-range flight. The sheer kinetic energy generated an equally devastating recoil stroke. A massive rearward force vector threatened to tear the gun from its mountings. This force was systematically absorbed by dual, over-engineered hydropneumatic cylinders. They compressed dense hydraulic fluid to mathematically dissipate the multi-ton shock. But internal buffers were not enough. At the tip of the barrel, fluid dynamics played a critical role. High-pressure exhaust gases were weaponized against themselves. A double-baffle muzzle brake mathematically redirected these expanding gases sideways and backwards. This action physically pulled the barrel forward, neutralizing a massive percentage of the recoil. As the gun returned to battery, the vertical block dropped, ejecting the massive spent casing, while ventilation vectors instantly cleared the toxic fumes. The Apex Predator was rearmed. To harness the apocalyptic power of the 8.8-centimeter gun, absolute optical precision was required. The gunner's zone was algorithmically optimized for targeting. Mounted within this space was the Zeiss TZ-F9D, a highly advanced articulated monocular telescopic sight designed specifically for long-range kinetic engagements. Unlike primitive optics, it featured an articulated linkage. As the massive gun elevated, the objective lens mirrored the angle, but the eyepiece remained mathematically fixed, ensuring the gunner's posture never shifted. Inside the optic, high-grade Zeiss glass refracted incoming light. Perfect mathematical ray tracing delivered variable magnification, yielding crystal-clear target acquisition at extreme distances. The reticle utilized stadiometric triangles. By aligning these geometric markers with a target of known size, the gunner could instantly calculate exact distances without external rangefinders. Upon ignition, the immense chamber pressure propelled the Panzergranate projectile out of the muzzle at a staggering supersonic velocity of 1,000 meters per second. This extreme velocity fundamentally altered ballistics. The projectile maintained a mathematically flat trajectory, practically eliminating the need to calculate shell drop at combat ranges. As the heavy penetrator crossed the 500, 1,000, and 1,500 meter marks, its immense mass mathematically preserved its kinetic energy against atmospheric drag. Even at the extreme standoff distance of 2,000 meters, the weapon retained a terrifying level of kinetic lethality. Upon impact, the hardened steel cap of the Panzergranate transferred its remaining energy into a massive, concentrated point, mathematically overwhelming the target's structural limits. The Vector easily punched through over 130 millimeters of armor at 2 kilometers. The resulting internal spalling guaranteed absolute target destruction. When graphed, the penetration capabilities of the KWK-43 rendered almost every enemy vehicle mathematically obsolete before they could even return fire. In open terrain, the Tiger II was not a brawler. It was an armored sniper. Its optics and ballistics created a geometric dome of control, extending well beyond 2 kilometers. From the front, the equation was flawless. Impenetrable sloped armor combined with an unstoppable kinetic weapon system. But a machine of this magnitude could not exist without consequences. The very environment it fought was mathematically incapable of sustaining its mass. While virtually invincible in combat, the Tiger II was rapidly defeated by its own logistical footprint. Routine maintenance was a mathematical nightmare. The extreme 68-ton mass exerted constant, punishing shear stress on the bearings. If a roller bearing shattered on an innermost road wheel, the true cost of the Schachtellaufwerk became apparent. A direct extraction was geometrically impossible. The dense, overlapping architecture mathematically blocked any lateral movement of the inner components. To access a single inner wheel, the maintenance algorithm dictated the mandatory removal of up to 5 massive, perfectly functional, outer and middle row road wheels. Before extraction could even begin, immense hydraulic jacks had to physically lift the 68-ton steel fortress off the earth. a perilous operation in muddy field conditions. Each wheel weighed hundreds of kilograms and was secured by massive torque bolts. Extracting them was an exhausting, time-consuming, geometric puzzle. By the time the inner bearing was accessed, the maintenance clock had consumed critical operational hours. This mathematical inefficiency drastically reduced the number of functional tanks on the front line. Beyond mechanical failure, the geometry itself invited environmental disaster. The tight clearances between the overlapping wheels perfectly trapped dense mud, rocks, and battlefield debris. When the ambient temperature dropped below zero, this trapped slurry crystallized. The liquid debris instantly transformed into a rigid structural solid. This created a complete kinematic lock. The wheels were mathematically welded together by the ice. The immense Maybach engine torque could not break the geometric freeze. Attempting to force the frozen tracks sent the kinetic energy violently backward. The incredibly complex, overburdened front transmission absorbed the sheer load, often resulting in catastrophic internal failure. Fixing this cascaded failure required the ultimate extraction. The entire front armor had to be unbolted, and the massive transmission block pulled completely out of the chassis. This was the geometric reality of the Tiger II, a flawlessly armored citadel, rendered entirely immobile and disassembled by the unforgiving physics of its own mass. The mathematical truth was stark. Operational availability rarely exceeded 40%. The greatest enemy of the King Tiger was never enemy fire. It was the engineering equation itself. Yet, when it did run, and when the terrain held its weight, the assembled machine remained the undisputed apex predator of the battlefield. The extreme mass of the Tiger II created a severe geographical paradox. It was not just an enemy to opposing armor, but an enemy to the infrastructure it drove upon. Standard European road bridges of the era were engineered to support a maximum structural load of roughly 24 tons. Approaching this infrastructure with a 68-ton vehicle resulted in a catastrophic mathematical mismatch. If a crossing was attempted, the sheer downward force immediately overwhelmed the tensile strength of the steel beams. The mathematical result was inevitable structural collapse, dropping the vehicle into the chasm below. Therefore, conventional bridge crossings were frequently denied. To overcome this geographic paralysis, the vehicle was forced to bypass bridges entirely, resorting to deep wading operations across riverbeds. Submerging a 68-ton electronic and mechanical vault required strict hermetic sealing. Every hatch was locked, compressing heavy rubber gaskets to create an airtight geometric perimeter. The massive Maybach engine still required oxygen to combust. A telescopic snorkel tube was erected from the rear deck, extending high above the turret roof. As the vehicle submerged, it became entirely reliant on this single vertical geometric link to the atmosphere. The entire armored volume was engulfed by hydrostatic pressure. However, pulling air through a narrow, restrictive tube choked the airflow. The V-12 engine suffered oxygen starvation, drastically reducing its RPM and power output just when it was needed most. Struggling with reduced torque, the 68-ton mass faced a saturated riverbed. The soft mud compromised the ground pressure equation, threatening to swallow the tracks entirely. This created strategic paralysis. Because standard bridges collapsed and deep wading was highly perilous, the deployment of the King Tiger was heavily dictated by local geography. It was the ultimate paradox, a machine designed to break through any defensive line, yet frequently rendered completely immobile by a simple stream. The King Tiger was a triumph of extreme metallurgical and ballistic engineering, but it was a fortress without a foundation, trapped by the mathematical realities of its own mass. A masterpiece of destruction, bound by the unforgiving laws of Earth and gravity. To fully understand the vulnerability of the King Tiger, we must look beyond its massive geometric shape and analyze the microphysics of the steel itself. At the molecular level, ideal armored steel relies on a perfectly balanced crystalline lattice, a geometric structure that provides both extreme hardness and vital elasticity. This balance required highly specific chemical alloys. Elements like nickel and molybdenum were mathematically essential to give the thick steel its crucial ductility, allowing it to flex rather than shatter. However, late in the production cycle, the logistical supply chain completely collapsed. Critical alloys like molybdenum were entirely depleted from the manufacturing equation. Without these elements, the fundamental geometry of the steel degraded. The massive 150mm plates achieved extreme hardness, but lost all elasticity. They became mathematically brittle. This chemical failure created a fatal physics loophole. When a heavy kinetic vector struck the exterior of the slope vault, the sheer thickness and slope of the geometry successfully defeated the projectile. 0 millimeters of penetration were achieved. But kinetic energy cannot be destroyed, only transferred. A massive acoustic and kinetic shockwave propagated directly through the brittle steel lattice. Because the degraded alloy lacked the elasticity to absorb this frequency, the inner face of the armor structurally failed. It literally shattered from the inside out. This phenomenon is known as spalling. Heavy chunks of jagged steel sheared off the interior wall, transforming into lethal, high-velocity shrapnel directly inside the sealed crew compartment. The impenetrable vault had become a fragmentation grenade. The meticulously engineered life support zones were violently intersected by the tank's own degraded material. The mathematical equation was unforgiving. When you subtract ductility from heavy kinetic impact, the result is catastrophic internal fragmentation. From the outside, the King Tiger often appeared completely undefeated, a flawless geometric silhouette bearing no penetration holes. But inside, the crew was eliminated. It was the ultimate demonstration that in armored warfare, perfect geometry is entirely useless without perfect chemistry. Despite these severe logistical and material compromises, the fundamental mechanical design of the machine remains a pinnacle of heavy engineering. This brings us to the ultimate mechanical logic chain. Individually, every subsystem of the Tiger II was an exercise in extreme, uncompromising engineering. The foundation was an unprecedented geometric footprint. 800mm tracks and overlapping road wheels mathematically dispersed a crushing 68-ton mass. Into this base dropped the overburdened heart, a 700-horsepower V-12 engine and complex transmission, constantly fighting a losing thermodynamic battle against the vehicle's own weight. Covering this machinery was the impenetrable vault, 150 millimeters of steel, geometrically angled to utterly defeat incoming kinetic energy. Seated upon the massive roof ring was the production turret, an ergonomically flawless command center, maximizing internal volume while eliminating frontal ballistic traps. Finally, the installation of the apocalyptic weapon system. The L-71 8.8-centimeter gun, the ultimate kinetic annihilator. When measured purely by combat metrics, the mathematical equation was absolute. Impenetrable armor plus extreme high-velocity firepower equaled absolute tactical supremacy. But war is not fought in a vacuum. When the factors of mobility, 68 tons of mass, and extreme logistical maintenance were added to the equation, the result was critical strategic failure. The King Tiger remains one of the most fascinating engineering paradoxes in history. A breathtaking masterpiece of metallurgical and mechanical design, crushed by its own uncompromising standards. It stands as the ultimate manifestation of the heavy breakthrough vehicle concept, a true mobile fortress. A design that fundamentally pushed the boundaries of what was possible with mid-20th century technology. This has been a mechanical deconstruction of the Tiger II. Subscribe to explore more extreme engineering and absolute physics in military history.